True confessions. I've always found the conjugate differential to be a little bit not necessary. I've never really had to use it much. And so I wanted to clarify why we have to do such a thing. So the situation that we have here is a harmonic function u. Now, it's easy to see using the Laplacian and polar coordinates that log r being the radius in polar coordinates, is harmonic. So I'm going to let u be log r. That's natural log. And if you look at the Laplacian and polar coordinates, then it's trivial that this function is harmonic. But it's also interesting to explore what happens if we look at this in Cartesian coordinates. And so what I'm going to do is, instead of using the simple polar coordinates, the reason we have polar coordinates is make things easier, but what I'm going to say is this, that in fact the log of r is the log of x squared plus y squared, well, a half, because I've taken out the square root. And I probably ought to put some parentheses here just to make things more definite. Okay, so is this harmonic? Yes, it is. And the only way, well, the best way to see it is to change into polar coordinates. But if you're going to do it in Cartesian coordinates, you're just going to have to take all the derivatives, which probably isn't that exciting on a video, but it's got to be done. So we take the partial of u with respect to x. So here's u 1/2 the log of x squared plus y squared. Well, that's a pretty simple derivative if you're into formal derivatives, because you just have to use the chain rule, and the 1/2 gets canceled out, and you end up with x over x squared plus y squared. Now, you've probably done enough integration that maybe an idea is appearing here, but we'll see. Anyway, and just by symmetry, the partial with respect to y is the same fraction except with a different top. So the bottom's still x squared plus y squared, and the top is y. So there is the first derivatives. And if we look at the second derivatives, because that's what the Laplacian says, it's a little funky, but hey, what can you do? So the partial of u with respect to x, well, there's it's a quotient, so we have to use the quotient rule. And trust me, the bottom isn't going to be relevant, so I'm just going to put that there's a square there. And so on top, you have derivative top times the bottom. Well, that's just x squared plus y squared, minus the top times the derivative of the bottom. And so partial x minus top times the derivative of the bottom, that looks like minus 2x squared. And if you do the same thing with the second derivative, again, the bottom isn't super relevant, so I'm just going to leave that out. And just by symmetry again, we've got x squared plus y squared minus 2y squared on the top. Now, if you add these up, you see the bottoms aren't going to matter. You're going to get an x squared and an x squared and a minus 2x squared. And you're going to get a y squared and a y squared and a minus 2y squared. So the Laplacian is 0, and this is a harmonic function. So there's the situation. So we have a harmonic function. Now, harmonic functions should have conjugates, and that's locally true, but let's see what happens in this case with the global situation. And so what we have here is the conjugate. Let's call it V, because that's pretty standard. So V is the conjugate. And I'm going to take advantage of the Cauchy-Riemann equations and say the partial of V with respect to y is the same as the partial of u with respect to x. So that's just half of the Cauchy-Riemann equations. I don't know if that's the Cauchy half or the Riemann half. Anyway, and we have an expression for that, so that is a fraction. It's got x squared plus y squared on the bottom, and it's got x on top. And this is what I was alluding to before. In order to figure out what v is, we have to take the integral of this with respect to y, and then there'll be some factors maybe left over that are x factors, but then, well, these things tend to work out. So I was alluding to this as an integral before. So what we want is up to terms involving just x. So I'm going to say modulo x. V is integral of this fraction x over x squared plus y squared dy. That's the partial of v with respect to y. And again, I've said modulo x. There might be terms involving x that come up. And if you're real ace at calculus 2, then you say, oh, that's just arctan of y over x. But let's go through that and see what goes on here. Remember, we're integrating with y as the variable, so x is a constant in this context. And so what we can do is, it can be a little bit messy, but I think it's worth doing. We can take some things out of the integral. I'm going to take out x over x squared. And what that does is that's cleared out the top with the factor of x. And on the bottom, I'm left with 1 plus something squared, and that's a fraction y on top, x on the bottom. I made that kind of small, but I think you can read it. Okay, so, and now if we look at and do a substitution, when you do a substitution, you always think, oh, I'm going to substitute u. Guess what? We've already used u. Guess what? We've already used v. So I'm going to make the rather flaky substitution of a is y over x. So dA, this looks weird, I know, is dy over x. Keeping track of what's a constant and what's not a constant there. And so when I do the substitution in this integral, what I have here is I've got dy over x. So this is just the integral of dA over 1 plus a squared. And this is it shouldn't be a surprise, especially after looking at the Laplacian and polar coordinates. It shouldn't be a surprise. It's not a surprise, but surprise! This is the arctan of y over x, commonly known as theta in polar coordinates. Well, isn't that just peachy? Theta is not a single-valued function. It's the argument. And if you go around, things keep changing with theta, and so we do not have a single-valued conjugate function. Oh, locally over here, in a little region, we have a single-valued conjugate function, but in the whole domain, which is everything except the origin, we do not have a single-valued conjugate function. So that's why we need the conjugate differential. So let me show you. First of all, theta is not single-valued, and if we look at what's going on here, we're kind of following what's on page 163 in Alfors. We have that dv, just in normal terms using the ordinary chain rule, is the partial of v with respect to x times dx plus the partial of v with respect to y times dy. So that's just standard advanced calculus. Now, we have the Cauchy-Riemann equations, and so what we have here is dv by dx is minus du by dy. That's u was our original harmonic function, and that's now that's the coefficient for the differential dx. uh, plus du by dx as a coefficient for the differential dy. And that's the conjugate differential. The problem is that this is well defined even if you don't have a global antiderivative. So this is the conjugate differential as defined on page 163 of Alfor's. And there's something perpendicular going on here, and Alfor's goes on to explain it. I'm not sure it's explained all that well. It involves a lot of multivariable calculus where you're looking at a level curve for u. He never says that, but you are. You're looking at a level curve for u, and you've got another curve, gamma, that crosses that level curve, and you're looking at the relationship between gamma and the gradient of u. The gradient is perpendicular to the level curve, and this comes out to be the directional derivative in the direction to the normal to gamma. So I might have to spell that out more specifically, but let's stop here and go on with our conjugate harmonic functions.